In this video, we are going to start developing the definition of the derivative, and we'll look at what's called the tangent line problem, which is directly tied to the derivative. Our learning objectives are: recognize the meaning of the tangent to a curve at a point, calculate the slope of a tangent line, identify the derivative as the limit of a difference quotient, calculate the derivative of a given function at a point, describe the velocity as a rate of change, explain the difference between average velocity and instantaneous velocity, and estimate the derivative from a table of values. So lots to do. We will start by just understanding where this notion of a difference quotient is coming from. What we want to start with is just thinking about this notation. We're taking a fixed point, which we'll call a f of a, and we're looking at close nearby points. So we can call the nearby point x, f of x, and using x indicates that we're going to allow it to change. So a will be a fixed point, a f of a, and x, f of x will be a point that's, we can think of it as being allowed to kind of slide around. Sometimes, instead of using x, f of x for that nearby point, we might use a plus h and f of a plus h. And when we do that, we call h the increment. So let's just make a quick sketch here. I have just a general function and a fixed point, an x value a, and then I would have the corresponding y value f of a. And I want to choose points close by. And I could call that close by point x f of x, or I could call it a plus h, f of a plus h. Either one is totally appropriate. If I use that h notation, then h is the distance I am away from a. Right, and h could be allowed to be negative, so that would tell us the signed distance away. If h is negative, then a plus h is actually left of a. And what we're trying to do is look at the quotient, the rate of the change in y divided by the change in x. So the change in y is always going to be a change in function values, and the change in x will just not involve the function values. And you recall that a change in y over a change in x is the slope. So what we're calculating here is the slope of the line that connects those 2 points, a f of a and x f of x, or a f of a and a plus h f of a plus h. That slope of that secant line is called the difference quotient, right? So we'll sometimes use q to represent it, or sometimes we'll use m sub and then sec to talk about the slope. That's what we usually use m for, and subscript secant line to remind us this is the slope of the secant line connecting 2 points. So sometimes we'll compute the difference quotient by doing f of x minus f of a over x minus a, and sometimes we'll do f of a plus h minus f of a over h. Notice this h is the same as a plus h minus a. So we're still taking a difference of x coordinates, but we can just simplify that to h. And like I had mentioned above, that is called the increment for that difference quotient. Okay, let's take a look at a specific example and see how this is going to look. So if I want to compute the slope of the secant line between 2 and 2.5 for this function, x squared minus 3x plus 1, let's do that. So we say the difference quotient is the same as the slope of the secant line, and we compute it by doing the change in x, the change in y, divided by the change in x. So we'll probably want to grab a calculator for the change in y, but this would just be 2.5 squared minus 3 times 2.5 plus 1 minus f of 2, and we need to subtract several terms, so I'm going to put some brackets there. 2 squared minus 3 times 2 plus 1, and then that's going to be divided by 0.5. And you can see 0.5, that makes sense as the change in x because that's how far I moved, right, to get from 2 to 2.5. So then I'm going to grab a calculator. And 2.5 squared minus 3 times 2.5 plus 1. And then I want to subtract 2 squared minus 6 plus 1. And I want to divide that by 0.5. So we get 1.5. Before we move on, I want to take a look at the graph of that function, but I'm going to use GeoGebra instead. And I have this function already entered in GeoGebra. So I've got x squared minus 3x plus 1. And I have set up for us a function that's going to show us the picture of the secant line for a fixed a value and a fixed h value. And then we'll be allowed to slide those around. So you can see here I set up as this function down below, g of x equals f of a plus h minus f of a divided by h. And you can recognize that as a difference quotient. And I don't have a fixed a value and I don't have a fixed h value. I'm going to let those slide around. And then next to that I have times x minus a plus f of a. And this is just exactly the, let's see, point slope form of the equation of a line. I have the slope times x minus a fixed x value, and then I'm adding the fixed y value. So this is going to show us the secant line between a f of a and a plus h f of a plus h. So right now I have my a set at 2, and if I want to move away to 2.5 as the other value, I better make my h 0.5. So I'm going to slide that. So and now I have set up exactly a picture of what we were asked to compute over here. So we were asked to compute the slope of this secant line, where one point is fixed at 2f of 2, and the other is fixed at 2.5 f of 2.5. Right, and we found that the slope of that line was 1.5, which means I should be able to go up 3 and right 2 and see another point on that line, and that looks right? It does look like that slope of that line is 3/2 or 1.5. So our goal is actually to find the slope of what's called the tangent line. So as I let these 2 points get closer and closer and closer, so as I let h get closer to 0, so smaller and smaller and smaller, we can see that it's harder and harder to distinguish the 2 points on the curve, and it starts to look like maybe it only, this line that we're calling the secant line, maybe that only hits the curve in one spot, right? And the closer h gets to 0, the more it looks like what we would call a tangent line, a line that hits our graph in just one point, at one point instead of at 2. So we just now computed the slope of a secant line, but our goal is to find the slope of what we would call the tangent line, which looks right about like this. Notice when I let h actually get to exactly 0, if I can here, that line disappears, which makes sense because my slope involved a 0 in the denominator, and if the denominator of my slope is 0, it's undefined. So I can't let h actually be 0, but I want h to be as close to 0 as possible, and we're trying to find the slope of that line. Okay, so let's move on to the next example. So just like we saw, we're trying to compute the slope of the tangent line. So we're letting those 2 points, a f of a and a plus h, f of a plus h, get closer and closer together. So we can picture that as looking at this difference quotient and letting either h go to 0, letting the increment go to 0, or we can picture it as letting x get closer and closer to a. Either way, we're looking at a limit, but it just depends on which form we're using, what we're going to set in front of that limit. Either x approaching a, to say the 2 points are getting closer together, or h approaching 0, also indicating the 2 points getting closer and closer together. So again, I'll just make that little sketch. And it doesn't matter what our function looks like, doesn't matter where a is. F of a is always a y value, and we're imagining that a and f of a are fixed, and I don't like that function. It just looks a little too flat right there. Let me change it. It was technically fine, but all right. And then we're taking a point close by, and we're either calling this x or a plus h, right? And this point then up here is either x, f of x, or a plus h, f of a plus h, right? And whether we say x is approaching a or h is approaching 0, we're going to be moving this direction, and our function value is going to move, well, the point we're looking at is going to move closer and closer to a f of a. And again, it could be that we're approaching from the other side, and we would still call this point x, f of x, and we would still call this point a, f of a plus, oh, excuse me, a plus h, f of a plus h. And this would just be imagining that h is negative, but if we let h go to 0, we'll still move this way. And x is less than a from this side, and x would be greater than a from the other side. So the next example asks us to find the equation of the tangent line to another parabolic function at a specific point x equals 1. We could also say a equals 1, but that's our fixed value. It says using the first formula for the slope of the tangent line. So we'll say the slope of the tangent line, we want to do the limit as x approaches a. In this case, a is 1, f of x minus f of a, so I'll write f of 1 divided by x minus 1. And so let's fill in these values. Limit as x goes to 1, f of x is 3x squared plus 2x minus 1, and f of 1 would be 5 minus 1, so minus 4, divided by x minus 1. So I filled in the formula for f of x, I filled in the number that represents f of 1, and now my denominator is x minus 1. If I try to do a direct sub to evaluate this limit, I get 0 over 0, which is an indeterminate form. So I need to do some work. And it looks like probably, since I have a ratio of polynomials here, I probably want to factor and reduce. So I've got 3x squared plus 2x minus 5 in the numerator, and x minus 1 in the denominator. And if I've done this correctly, I'm hoping for a factor of x minus 1 in the numerator. so that I can cancel that with a factor of x minus 1 in the denominator. So let's see if this will work. To get a negative 5 on the end, I must need a plus 5 here. And to get a 3x squared at the start, I would need a 3x at the start. And that's going to give me a negative 3x plus 5x, so 2x in the middle, which is exactly what I want. So great, we are able to factor that. And as long as we're looking at the limit as x goes to 1, we're able to simplify this here, because we're only looking at points that are close to 1, not exactly at 1. So this limit will be the same. And now we have a limit which we can evaluate by direct substitution. So we're finding that this limit is 3 plus 5, that's 8. So they were asking us to find actually not just the slope of the tangent line, but the equation of the tangent line. So what we want to remember is, so far, what we computed, it would be the slope of the tangent line. We need to review equation of a line. It's typically going to be useful for us to use point slope form rather than slope intercept form, because most of our problems are going to be such that we have the slope and we have a point on the line, but we don't necessarily have the y-intercept. So most of the time you're going to want to use point slope form, and often we're actually going to want to use a slight rearrangement of that. We are going to want to move the y1 to the other side. So we can say the y is equal to the slope of the tangent line times x minus a, will be our fixed x value, plus our y1, which will be the y coordinate at our fixed point. So this is the format we will want to use for the equation of the tangent line. So for this particular problem, we will want y equals, we figured out the slope of the tangent line was 8, and our fixed x coordinate was 1, and we determined that f of 1 was 4. So let's take a look at the graph of f along with the graph of the tangent line and see how it looks. I'm going to, let's see. So we had y equals, clear these. Let's turn them off for now. Let's see. We had y equals 3x squared plus 2x minus 1. And we came up with this tangent line was 8x minus 1, was it? Yes, plus 4. And we want to see those two together. So let's take a look at the graph. And I could manually adjust my window, but I think I'll do that. Getting closer here to what we want to see. All right. So I can see that it looks like I have a function and its tangent line, and it looks like the x-coordinate of that tangent point is 1, and it looks like the y-coordinate of that tangent line being 4 seems reasonable. Everything looks the way we want it to look. All right. back to our notes. The next one, find the equation of the tangent line to the same function at the same point using the second formula for the slope of the tangent line. So we'll say, well, hopefully we'll get the same value, but let's see how this looks using the second formula. And the second formula said, let's do the limit as h goes to 0, f of a plus h minus f of a divided by h. And so we want the limit as h goes to 0. A is 1, so we'll have f of 1 plus h minus f of 1 divided by h. And again, we'll rewrite limit as h goes to 0. F of 1 plus h will look like 3 times 1 plus h squared plus 2 times 1 plus h minus 1. And f of 1 we've already computed, that's 4. So minus 4 and then divided by h. And again, if I try direct sub, I'm going to get 0 over 0. So we need to do more work in computing this limit. So we'll expand the numerator carefully. Anytime I have that binomial squared pattern, we have the square of the first plus 2 times the product of the two plus the square of the second. Now I'll distribute the 2, and I'm going to combine these two, so minus 5 now. And we'll keep going. Simplifying this numerator, I can see I have 3 plus 2 minus 5. So those are going to cancel out. I have 6h, and I have plus 3h squared. And then I have, it looks like another plus 2h. Right, and again I have plus 5 and minus 5. I'm not going to write those. And then divided by h. And now I can see I can factor out an h from the numerator, and then I'll have something I can use to compute the limit. If I factor out an h, it looks like I have 8h altogether there, so I'm going to combine those and make this h, and then 8 plus 3h as the second factor, divided by h. And that's that form we like to see where we can reduce. And now I have the limit as h goes to 0 for 8 plus 3h. Now I can do a direct substitution and I get 8. So again, there's the slope of the tangent line. And I want the equation of the tangent line. And I will rewrite this. We want to use the pattern y equals the slope of the tangent line times x minus a plus f of a. And this will look exactly like it did last time, because we got the same slope and the point will be the same. So 8 times x minus 1 plus 4. And we won't look at the graph again because it'll be exactly the same thing. So you can just see there are 2 ways to compute the slope of that tangent line. It's important to be familiar with both ways, both of those formulas, and you can see we're going to get to the same result, but the process along the way is going to look a little bit different. Okay, then find the equation of the tangent line to a new function, 2 over x minus 4, at x equals 2 using the first formula for the slope of the tangent line. So back to formula 1. So first we want the slope of the tangent line is going to be the limit as x goes to a. So again, in this case, this is our a value, the fixed x. So the limit as x goes to 2 for f of x minus f of a, so f of 2, over x minus a, so x minus 2. And this will look like limit as x goes to 2. F of x is 2 over x minus 4. F of 2 is 2 over 2 minus 4, so 2 over negative 2, so negative 1. And x minus 2 is just going to stay x minus 2. I'm going to rewrite minus negative 1 as plus 1. And then I'm going to choose how I'm going to simplify this complex fraction. This time I think I'm going to multiply the numerator and the denominator by the LCD, which would just be x minus 4, because in the denominator of the denominator is just 1. So I'm going to multiply in the numerator by x, not plus 4, x minus 4, and in the denominator by x minus 4. So again, I'm multiplying by a form of 1 that's going to allow me to clear out these fractions. When I do that, I'm going to distribute. And from that first product, when I multiply x minus 4 with that first term, I'm just going to have 2 left. And so I'll have 2 plus x minus 4 divided by x minus 2 times x minus 4. And I always leave that denominator factored because my goal is to eventually reduce that factor of x minus 2. And I'll be able to do that in the next step. I can see because my numerator now simplifies to x minus 2. So now I can reduce these two factors. And now I have the limit as x goes to 2 for 1 over x minus 4. And this form is one that allows me to do direct substitution. So now I can just say this is 1 over negative 2. So negative a half for the slope of the tangent line. And we want the equation of the tangent line. So the hard work is finding the slope, the equation of the tangent line. We go back to y equals the slope of the tangent line times x minus a plus f of a. And for us, a was 1, and we already, a is 2, and we already computed that f of a is negative 1. So we'll have y equals, we found the slope to be negative a half, a was 2, and f of a was negative 1. Or we can rewrite y equals negative a half, x minus 2 minus 1. And it's certainly fine to distribute your slope through there and combine the constant terms, but it's fine to leave it just like this as well. Let's take a look at this graph just to make sure it all looks good. I'm going to use GeoGebra this time. Let's turn off those others and add a new input. So I want f of x to be 2 over x minus 4. So there's my function, and we found the equation of the tangent line to be negative 1/2 times x minus 2 minus 1. Right, and I can see from this picture that this looks good. I can see that point of tangency marked there, and this tangent line looks just like we want it to look. So looks like our work was probably good. On to example 5, find the equation of the tangent line to now a square root function at x equals 7 using the second formula for the slope of the tangent line. So back to formula 2, and that says the slope of the tangent line is the limit as h goes to 0, f of a plus h, so in our case that's going to be f of 7 plus h, minus f of a, so minus f of 7, divided by h. So I'll have the limit as h goes to 0, square root of 7 plus h plus 2, minus f of 7, which would be the square root of 9, so minus 3, divided by h. And we remember from the last chapter, when we have something like this, where we've got a difference quotient that is a 0 over 0 form, which it will be if we try direct substitution, and it involves a radical, we want to multiply by the conjugate of that radical expression in the numerator and the denominator. So we leave the radical itself unchanged. We change the sign between the two terms, and then that's the factor we use for our multiplication. We continue to leave the denominator factored, but we simplify the numerator. In the numerator, we want to use a squared minus b squared pattern because we have a product of a sum and difference of the same terms. A squared will just be that expression inside the radical, so 7 plus h plus 2, and b squared will be 9. So now our numerator we can see simplifies to just h. So I have h over h times square root of 7 plus h plus 2 plus 3. And now I can reduce my h over h, so I no longer have an h in the numerator, now I just have a 1. And I also no longer have an h in the denominator, so when I try to substitute h equals 0, I won't have this 0 over 0 problem anymore. And when I do my direct substitution, I have 1 over square root of 9 plus 3, so 1/6. And again, this is the slope of the tangent line, and I want to put together the equation of the tangent line. And now that we have the slope, it'll be easy to put the pieces together. So I want y equals the slope of the tangent line times x minus a plus f of a. So y equals 1/6 times x minus 7 plus f of 7, which we computed to be 3. And again, let's take a look at the graph and make sure it looks the way we want it to. So we had our function this time is square root of x plus 2. And the tangent line we computed was 1/6 times x minus 7 plus f of 7, which we computed to be 3. So we've got the square root function that was shifted to the left. So let's go find that up here. So we can see we've got a line and a square root function. And it certainly looks like that function and the tangent line meet up where we want them to. Right, so our tangent line, or tangent point, was 7, 3. So you can see here in this window, 7, 3 looks like they line up, and they are not actually the same thing, but once we zoom in close enough, the line and the function look almost identical. So it looks like our work was correct. So I will stop this video here, and in the next video we'll finish looking at the derivative using this limit definition. The slope of the tangent line that we were computing in the last video can have a different meaning depending on what our function represents. And some of those meanings can be velocity or acceleration in physics, marginal profit functions in business, or growth rates in biology. In this course, we're going to focus more on the velocity and acceleration and growth rates as our applications, and we're not going to focus as much on the business applications, but those functions are more the focus for our Introduction to Calculus course, Math 1120 at our school. When we're finding the slope of the tangent line, what we're actually finding is what's called the derivative. And so the process for finding the derivative is called differentiation. So we're going to keep computing these slopes of the tangent lines over and over and over, and we're going to call them the derivative for the function at a point. So here's the definition. The derivative at a point is the limit as x approaches a, f of x minus f of a over x minus a, and you would say that's exactly the same as the formula for the slope of the tangent line, and you'd be correct. But now, instead of writing m sub tangent, we're going to use this notation f prime at a. So that little tick mark, we read that as prime. So f prime at a means the derivative of the function f at x equals a. Right? And we would say this is the same as the slope of the tangent line to that function at x at a f of a. Or we can say maybe we want to use the other formula for the slope of the tangent line, and we would say that's f prime of a equals limit as h goes to 0, f of a plus h minus f of a over h. So again, same as formula 2 for the slope of the tangent line. Exactly the same formula, but now we're calling this the derivative of a function. So example 6 says, here's a function, f of x equals 2 minus x minus 3x squared. Find f prime at -1. And it makes no indication of which formula we should use, so we can pick. We'll just use the first one. So I'm going to say f prime at -1 is the limit as x goes to -1, f of x minus f of a, so f of -1, divided by x minus a, so x plus 1. And I'll rewrite the limit. F of x is 2 minus x minus 3x squared, and f of -1, I'm just going to write it 2 minus -1 minus 3 times -1 squared, and then I'll compute it on the next line, divided by x plus 1. So now I have the limit as x goes to -1, 2 minus x minus 3x squared. Let's see, minus 2, that's 3 negatives on that one, so minus 1. And let's see, -1 squared is 1, so minus -3, so plus 3. So that looks like I have in my numerator let's see, positive 5 minus 3, so that's going to be a 2 minus x minus 3x squared. Over x plus 1, and I'm hoping that I can factor and reduce, so let's see what we can do here. I don't generally like to factor things that have a negative coefficient on the x squared, so I want to factor that negative out and rearrange things here. So I'm going to do this. I'm going to factor out a -1, And that leaves me with 3x squared plus x minus 2 keep rewriting this limit until I'm able to reduce that x plus 1 factor. I'm going to keep my negative out here. And let's see if this will factor. I'm hoping for a factor of x plus 1, so I'm going to write that down first. If I have a factor of x plus 1, I'm going to need a minus 2, and I'll need a 3x here. That gives me a minus 2x and a plus 3x for a plus x in the middle, so that's exactly what I want. And now I can reduce x plus 1 over x plus 1. And so now I have limit as x goes to negative 1. And I can directly substitute, so I've got an opposite of negative 3 minus 2. Looks like that should be 5. And just for good measure, let's double check what the equation of the tangent line would be, even though it wasn't asked. We would put together y equals, and instead of writing m tangent, now I'm going to write the derivative, because that is the slope of the tangent line, at negative 1 times x minus a, so x plus 1 plus f of a, which we came up with as 0, it looks like. So if we've done this correctly, our equation of the tangent line should look like 5 times x plus 1. So let's take a look. So now we have 2 minus x minus 3x squared. So there's our parabola, and we want 5 times x plus 1. And that looks good. We've got a tangent at the point negative 1, 0. Looks like slope 5, looks like it's probably just right. Perfect. One more problem similar to those we've been doing. Now we want f of x equals square root of x minus 2, and we want f prime at 6. So we'll say f prime at 6, and let's use the second formula. This time will be limit as h goes to 0, square root of x plus h minus 2. This is not correct. We want a 6 here instead of an x. We want f of a plus h. So f of 6 plus h minus 2 minus square root of 6 minus 2 divided by h. So again, just a reminder, this is f of a plus h, and our a was 6, and this is f of a. So now I can see I'm looking at limit as h goes to 0, square root of, that would be 4 plus h, minus square root of 4. Square root of 4 is 2. And I can see that I need to rationalize here, so I will multiply by square root of 4 plus h plus 2. Make sure we change the sign in between those terms. And in the numerator, I'm going to establish that I have an a squared minus b squared pattern. And so that's going to leave me with 4 plus h minus 4. And in the denominator, I have h times 4 plus h plus 2, square root of 4 plus h plus 2. Always leave the denominator factored, simplify the numerator, and then we're going to be able to reduce our factor of h over h. And when we do so, we'll have a 1 now in the numerator. And we are allowed now to directly substitute, and we'll see we have 1 over square root of 4 plus 2. So 1/4. So again, let's take a look at the equation of the tangent line. And I'll use y equals the slope. So instead of writing m tangent, I'm going to write the derivative, not the derivative at 1/4. It is 1/4, but it's the derivative at 6 times x minus 6 plus f of 6. So filling in our specific values, we'll have 1/4 for the derivative value times x minus 6, and f of 6 was 2. And let's just graph it to make sure we didn't make any errors. All right, so now we have square root of x minus 2. I'll get rid of those two functions, and then we're going to slide over a bit because we want the tangent line at 6 f of 6. And if we've done things correctly, which it looks believable that the slope of that tangent line could be 1/4, so that's good. We have 1/4 times x minus 6. And then we want to add to that 2. Perfect. You saw, hopefully, that line, the second line there, that we wanted to be the tangent line, looks like it certainly could be the tangent line at 6, 2. Okay, now we have a function, it looks like a piecewise function, and we want to find f prime at -3 and f prime at 1.5. Right, so we want to just remember that f prime at -3 is the slope of the tangent line at -3 f of -3. So if I go to -3 f of -3, I can see that this line is actually just linear. And so for a linear function, the slope of the tangent line is just the slope of the line, because the tangent line would actually just be the same as the line itself. So for a linear function, the slope of the tangent line is the same as the slope of the line itself. So for f prime at -3, I'm just thinking, well, what's the slope of that greenish line? And that slope should be 0 because the y values are not changing. So change in y is 0. So the slope for that line is 0. And then we're also asked to find the slope or the derivative at 1.5. So f prime at 1.5, I'll go to 1.5 f of 1.5, and I can see again this is linear. So the slope of the tangent line is the same as the slope of the line itself. And it looks to me like that's slope 2. I'm going up 2 and right 1 between points. So the slope is 2. So the derivative is 2. And as we were mentioning, or as I was mentioning at the start of this video, one of the applications of the derivative is to talk about velocity, right? Because velocity is the rate of change of a position function. So just a reminder that if s of t, which is the standard notation for a position function, if s of t is an object moving along a coordinate axis, or just really any straight line, the average velocity of the object over a time interval from a to t would be a fixed, or like a changing amount of time, right, is given by this difference quotient. The average velocity is s of t minus s of a divided by t minus a, right? So change in position over change in time. right? So position might be labeled in feet or inches or some distance quantity, right? And time will be in a time quantity. So we might have feet per second or miles per hour or inches per minute, right? That would be the label on the average velocity. And then it says as values of t approach a, approach our fixed value, then the average velocity turns into what we call the instantaneous velocity. And so we will use v of a, or v at a, and that's the derivative of the position function at a. And we'll say that's the limit as t approaches a, s of t minus s of a over t minus a. Or we can also use limit as h approaches 0, s of a plus h minus s of a divided by h. That would also work, right? Either formula for the derivative will apply here. But the point is the derivative of a position function is the velocity function. So in example 9, we're given that a rock is dropped from a height of 64 feet and its height above ground at time t seconds later is given by s of t equals negative 16 t squared plus 64, at least for t between 0 and 2, because at 2 seconds you can figure out that the rock is going to hit the ground, and so it will stop falling at that point. Part A asks us to find the average velocity between t equals 1 and t equals 1.5 seconds. So for the average velocity, it's the same as the slope of the secant line. We take the change in y over the change in x, or the change in position over the change in time. And so we want s of 1.5 minus s of 1, so a difference in positions, over the change in time, which will just be 0.5. So I want negative 16 times 1.5 squared plus 64 minus negative 16 times 1 squared plus 64 divided by 0.5. Right, so the label on my numerator will be feet, and the label in the denominator would be seconds. And this is looking good because I want the velocity label to be something like that, feet per second. So I'm going to need a calculator. I have negative 16 times 1.5 squared plus 64 minus negative 16 times 1 squared. I'm not going to type that, plus 64. I can see that the 64 minus 64 will cancel out to 0. So I've got negative 20. That makes sense because the position should be dropping, and divided by 0.5. So it looks like negative 40 and feet per second. So it's important to recognize that velocity is slightly different from speed. Speed we would never list as negative, but velocity we will list as negative because that tells us the direction, right? So v average that's less than 0 tells us the direction is downward. If our axis is set up so that positive is up and negative is down, we might be moving horizontally, in which case you'd have to identify the positive direction of motion and the negative direction of motion. But a negative velocity just tells you that you're traveling in the direction that's set up as the negative direction. In this case, that would be downward. So the rock is falling at that point. It's dropped from a height, so it's falling the whole time. And between 1 and 1.5 seconds, the average velocity is negative 40 feet per second. Then we're asked to find the instantaneous velocity 1 second after it's dropped, and that we would label as just the velocity at 1 second, and that's the derivative of the position at 1 second. And let's use the limit as t approaches 1, s of t minus s of 1 over t minus 1. So we'll use the first formula there. And so we have the limit as t goes to 1. S of t is negative 16t squared plus 64. And s of 1 is negative 16 plus 64, so 48. All right, so now I've got limit as t goes to 1, negative 16t squared, 64 minus 48, that's plus 16. And I have a t minus 1 in the denominator. I can see if I just try to do a direct substitution, I'll have 0 over 0, so I need to do some work. And so I'm going to factor out a negative 16. And that's going to leave me with t squared minus 1. And now I can factor my numerator. Negative 16, that's t minus 1 times t plus 1. And now I can reduce t minus 1 over t minus 1. And I can substitute now, do a direct substitution, and I have negative 16 times 2. So negative 32, and I would still have feet per second because the change in my numerator was a change in position, which was in feet, and the denominator was a change in time, and time was in seconds. So the instantaneous velocity at 1 second is 32 feet per second. And the average velocity over that time interval that was length half a second was a little bit faster than that, right? Still in the same direction, but negative 40 feet per second instead of negative 32 feet per second. But it's good to see that those are relatively close to each other. A half second is a pretty long time interval, so we wouldn't expect these to be, close to the same. But if, one was like negative 1 feet per second and one was negative 32 feet per second, we might think maybe there was an error somewhere. Okay. Next one says, suppose that n of x computes the number of gallons used by a vehicle traveling x miles. And then it says, suppose the vehicle gets 30 miles per gallon. And part A just asks us to find the mathematical expression for n of x. So how many gallons has it used if it travels x miles? So if we think about the units we want to get to here, x is in miles, and I want to get to gallons. And I have a known ratio, 30 miles per gallon. I want the miles to cancel out and leave me with gallons, so I better put miles in the denominator and gallons in the numerator. So I get 30 miles per gallon, and now I can see that what I want is to do x divided by 30. So I can see n of x is going to be x over 30 gallons. Then we're asked to compute n of 100. That would just be 100 divided by 30. So, 3 1/3 gallons. And then explain the physical meaning. So we would think, well, this 100, what was that? That was an input, so that's a number of miles. So after traveling 100 miles, the vehicle has used 3 1/3 gallons. right? So this function n just tells us how many gallons have I used if I've traveled this many miles, right? And now we want to think about the derivative for this function at 100, right? And that's going to be the limit as, let's say, let's use the second definition. Limit as h goes to 0, n of a plus h, so n of 100 plus h minus n of a, so n of 100, divided by h. Let's think about what the label is going to be. So the numerator is a change in n, and the label on n is gallons. And the denominator is a change in the input, so per mile. So we want to think the label on this is going to be gallons per mile, and that's going to help us with the physical meaning. All right, so let's do the computation. Limit as h goes to 0, n of 100 plus h, that's 100 plus h over 30, and then n of 100, that was 100 over 30, and we still have divided by h in the denominator. That first fraction in the numerator, I can rewrite that as 100 over 30 plus h over 30. 100 over 30 minus 100 over 30, that's going to cancel out. So I really just have h over 30 over h, which is the same as limit as h goes to 0, h over 30 times 1 over h, because dividing by h is the same as multiplying by 1 over h. And I can see that I just have 1 over 30. Which makes sense, right? Because this is really just a linear function. It's 1/30th times x. And the slope of that function would be 1/30th. And we said for a linear function, the slope and the derivative should be the same thing. So it makes sense that we're finding that the derivative is 1/30th. And that really doesn't depend at all on the 100. We're going to get that same slope no matter what the a value is, because the slope of this function is 1/30th at every point, right? So 1/30th gallon per mile, right? And so the derivative here, the physical meaning, says when we've traveled 100 miles, we're using gas at a rate of 1/30th gallon per mile. And again, there's nothing really that would be different if we had traveled 200 miles or 1,000 miles. We're using gas at the same rate. Okay, then the last example here, we see we don't always have a formula for a function. Sometimes we have just some measured data points, and that's what we're going to look at here. Well, if we have these data points, we can still use the information to estimate the derivative of a function at a point. But again, it'll be just an estimate. But oftentimes that's good enough. Right? So what we have in these two tables, one table gives us observed velocity of a car at various times. The times are listed in seconds, and the velocities are in feet per second. And we're trying to use those to compute the average acceleration, and that's going to be the change in velocity. Let me write. Per change in time, because acceleration would be feet per second, right? So if we want to know how is the velocity changing, am I getting faster at a faster rate or faster at a slower rate? We will do change in velocity over change in time. So we're going to estimate these over different time intervals between t and 19.96 seconds for values of t that get closer and closer to 19.96. So over on the second table, we'll make those computations. So we can see that the velocity for this vehicle is increasing as the time increases, and we just want to know what's going on with the acceleration. So these will be estimates of acceleration on this table. Right, and we're going to be looking at the average acceleration on different time intervals as those time intervals get shorter and shorter, and as the start of the time interval gets closer and closer to 19.96. So in the first one, I want to compute v of 0 minus v of 19.96 over 0 minus 19.96. So v of 0 is 0, and v of 19.96 was 337.19. And then in the denominator, I'm going to have negative 19.96. Right, so we'll find that number. And then in the second cell here, I'm going to do v of 3.05 minus v of 19.96. And then I want, in the denominator, 3.05 minus 19.96. And really, it doesn't matter the order we choose here. We could change the order of subtraction in the numerator and also change the order of subtraction in the denominator so that both of them are positive. We just want to make sure that we keep the order the same. So if I choose to put 0 as the first t value in the numerator, I better put 0 as the first t value in the denominator. Okay, so let's continue here. So v of 3.05, that was 88. And then 19.96, the velocity isn't changing. That will be the same in each of these. And then we'll have 3.05 minus 19.96. All right. So we see this pattern, right? We're taking the velocity at a certain time. The next one is 5.88 seconds, so that's going to be 147.67 minus the velocity at 19.96, which was 337.19, and then we'll have divided by 5.88 minus 19.96. And the last one, we'll take the velocity at 14.51 seconds, which was 293.33 minus the velocity at 19.96. And divide that by the change in time. So obviously we're going to need a calculator. So the first one, 0 minus 337.19 divided by negative 19.96. The first one we get about 16.89. And this would be feet per second per second. The next one, I'm coming up with 14.74, we'll say, feet per second per second. And then I've got 147.67 minus 337.19 divided by I'm getting 13.46 roughly feet per second per second. And then the last one, I'm getting 8.05. I'm going to double check that one. That one just seems so far away from the others, so I'm going to compute it again. So 293.33 minus 337.19 minus, nope, divided by 14.51 minus 19.96. And I think I forgot my parentheses at the start. Oh. I'm just going to clear that and try again. And hopefully the number that we had the first time was right, but I don't want to end on an error here. Yep, looks like that's right. So as it looks like our best estimate for the average or the acceleration at 19.96 would be something closer to 8. These are all decreasing, right? But at least we were successful in computing the average acceleration over those time intervals. So we can't compute the instantaneous, but we can at least see the trend here. Okay, so I guess that's the end of that section. We are starting to see how the derivative is going to show up in applications and the new notation for the derivative and the slope of the tangent line.